device is just very much like communications within a city, where the cars and people and buildings is quite similar. But I would like to draw your attention on the importance of being small. For example, you have a traffic accident with a bus or a truck, and people will get killed. But a virus, something very, very tiny, can kill billions. So the body and its elements have very, very different rules, like quantum physics and Einstein physics have very different rules. And our thesis is that targeted healing, when focusing on the molecular causes of a problem, can be far more effective. And also, the other principle is that time reversal is only possible with molecular mechanisms. For example, if you lose an arm or a leg, you don't grow another arm. However, the free radicals, for example, if they gain an electron, they turn back into a stable molecule. They go back in time where they used to be a stable molecule before they lost the electron and became free radicals. Same thing with ATP, it loses a phosphate and becomes ADP, that means diphosphate. The same thing with G proteins, GMP turns to GDP to GTP and so on and so forth. And they keep going in this sequence back and forth in time routinely. Now, a very important thing that you need to focus again is that the rules that govern young people and old people are very, very different. And there is a new theory of anti-aging, it's a semi-programmed theory of anti-aging. George Martin said that the brightest flame casts the darkest shadow. So the very same signaling pathways that would make us, that were very adaptive in our young age, when they aimlessly continue, they turn against us, they become a problem. And basically what this is about is an inertia, biological inertia. And inertia and stability are synonymous in this particular case, because you want stability, you want the system to be stable, you want the biological system to be stable, you want the personality to be stable, you want your relationship to be stable. However, when that aimlessly continues, you have problems with basically personality rigidity, with systemic rigidity, with relationships. When they keep going on and on and on, despite the fact that they are not longer adaptive, then that is a problem. And here is different theories of aging. The programmed, of course, says that you will have to live and die, and that is that basically. So there is a destiny involved there. And then you have the stochastic theories, where basically there's a functional decline that can be reversed by repairing the mechanisms that have subsided. And then you have the quasi-programmed that I just spoke about, where it's a hyperfunction, where things keep going aimlessly when they should not be going on anymore. And here, you need to shut down certain signaling pathways in order to enhance longevity. So, for example, inflammation is an example of that. Inflammation is very good for the young, but it's deleterious to the old, and then they can create different diseases like diabetes, heart disease, etc. Here we have sort of a summary of how you can increase longevity by decreasing certain mechanisms. And I have enumerated certain of the mechanisms that need to be decreased. I'm going to be talking more about the TOR signaling pathway, decreased insulin pathway, other pathways have to be decreased. And then you have the GNK pathway. I'm going to speak about that a little bit more later on. The sirtuins, histones, all that also need to be increased in order for longevity to be enhanced. So it's a combination. It's not always more. More is not always better. This is the 2019 Nobel Prize in Physiology and Medicine, where these investigators found that if they stop the brakes of the immune system, the CTLA-4 and the PD-1 are brakes that the immune system has. When you suppress these mechanisms, then the immune system can attack cancer, and it can actually, they feel that is the new theory, the new kind of method of that can cure cancer. Sorry, this is the mTOR pathway, mammalian target of Rhabdomyces, and that is for growth, but it's also for senescence. It starts enhancing growth, but past a certain point, it is deleterious for our health. And the PI3K pathway is also for cell growth, cell proliferation, cell differentiation, cell motility, cellular survival, and that is the good aspect. Now you see another image with it's the two sides of the same coin. Some of it is the good aspect, and then you have the bad aspect, the same pathway that is so important in cellular proliferation. It also induces the free radicals, free radicals that are deleterious to our health and also enhance aging. Now, the same thing with oxygen. Oxygen is necessary for life and energy production. However, by the same token, oxygen metabolism can create an instability in the oxygen molecule that will try to attract more electrons and to create dangerous properties such as peroxide anion radical or the peroxide. Reactive oxygen species, as well as exogenous damage like chemicals and UV radiation, can cause DNA lesions. I'm going to talk more about that tomorrow on the DNA lesions. They can basically cause telomere shortening, mismatch of DNA, double-strand breaks, and of course that leads to aging, disease, and death. And here we can have a combination of how you can reverse that. So basically, the global methylation we need to reinforce, the local methylation we need to suppress. And histones are the chromatin proteins that package DNA, and certain histones we need to suppress, others we have to reinforce. The same thing with chromatin remodeling. Chromatin is like a librarian, takes all the genes that are scattered and puts them back in place, like the librarian puts the book back in place for the DNA molecule to function properly. And then some of them we have to reinforce in order to kind of combat the aging process. So it's a combination of different pathways and how these pathways have to be targeted. Now, proteins communicate with each other. You can see here sort of a protein communication within different cells. This is the cells, this is the protein, and this is the proteins outside the cell. And what happens is that the cells communicate through their proteins. The proteins is the communicator of the cells. And the cells take these protein signals from inside the cell and from between cells and integrates it. Like our brain takes different language signals and integrates them into concepts. Since 2006, we know that aging is the result of disorganized protein-to-protein communications and also less communications within and between cells. You can see here's a young cell and an older cell with much less communications in the older cell. And proteins you can divide them into sensory action and chaperone proteins. Action are the proteins that do the action, sensory the ones that sense, and chaperone are the managers. Basically, this is a protein here, a calnexin is the chaperone protein. Now, the cells use signals to communicate, to fulfill functions, and very interesting, there's a lot of research. Again, this is 2 Nobel Prizes from 1998, 1999, where they found that the cell doesn't only change functions within itself, but it changes functions within other cells through this communication. And that cells carry billions of proteins in about 100,000 billion cells are targeting different cells and they're carrying messages that basically are like emails that or like messages like that with zip codes that get the messages to other cells. And what we found, new research has shown, these neural signals are based on compression, like sound waves, that basically the cells do not have to be in close proximity. They can be in distant proximity and still get these communication signals. And we have the glial cells that communicate like cell phones, and we have, of course, the neurons that communicate like landlines. And here you see, what you see here is you see signaling communication under the microscope. These are very, very distant cells. And you see this resonance situation here that is happening despite the fact that these cells have no proximity. They communicate from the distance. And there is a lot of articles that talk like the psychic cells, how the cells communicate from the distance, and how they are actually can even communicate through barriers. This is a research by Norris from 2013 until 2018, and I believe it's still ongoing, on how they had barriers, and they saw how the cells inside the barrier were actually altering the function of the cells outside the barrier, even though there was a barrier between them. This is a study on resonance, and how these investigators showed how resonance signals can actually alter functions within cells, and we're going to see some more of that later, and also my lecture tomorrow. And specifically, how does signaling affect wounds, for example? The JNK signaling pathway, remember I spoke about that before, is very in the center of this wound healing. There has been a lot of research on that, and there is a lot of statistical studies that show statistical significance of before and after of the wounds. And here you see an untreated wound under the microscope, and a treated wound. You can see how much, obviously, much greater improvement after 12 hours through this reinforcing the signaling pathway of JNK. Another aspect is DDR2, the collagen, this type of cellular signal that passes binding to DDR2 collagen receptors significantly enhance healing. So you look at certain receptors, and you look at, of course, certain signaling pathways like the JNK. Now, connexins are very, very important here. So downregulation of this, the connexin 43 and 26 has been associated with enhancing healing of wounds. And this is some clinical studies on wounds. This is immediately after the signaling approach, and this is a week later. This is another signaling study on 15 treatments. This man was told he will never grow nails, and actually there was quite significant healing. Diabetic healing of diabetics by Norris Lambert. He's a dermatologist in the Netherlands. And necrotic wound, this is a liposuction wound that was necrotic, and after 6 treatments you could see an improvement, a shortening, and also you could see more alive aspects. Burns, the connexins 43 that I spoke about it, they're also involved in the burns. But with the burn, sometimes you want to increase the deadening of the area, because that debris will help in the healing process. But basically what you see here is that as soon there is a burn, there is an increase of the connexin 43. You can see it here from there, how it increased and how there is cellular apoptosis as a result of increasing the connexin 43. This is the aspects of basically healing of the wound, and you see the inflammation takes over, and then proliferation kind of to start healing the wound with mesenchymal cells and stem cells, and you can see here an unhealed, non-complete modeling, and the complete modeling, and basically signaling will affect, will decrease inflammation and will increase proliferation, and of course that will lead to tissue injury. And you see here a control and a treatment group. You can see how much obviously better healing in the treatment group than the control group, and different arrows show the fibroblasts and inflammation and other aspects. Now, the thing I would like to leave you with is that the answer is not in the element, it's also in the age and the context. So you see here is, this is the number of references for different results. Some of it is completely unknown, some of, for the calcium, for example. Some of it, they find that there is regeneration. Others find the actin polymerization. Others find that there is increased inflammation as a result of that. It's the same thing with the ATP. ATP has much better results, of course, because it's the energy. But research is very conflicted. It gives you one result, and then it tells you the exact opposite. So it's very difficult to put, everybody sees a different part of the elephant. One person sees the trunk, the other person sees the tail, and nobody sees the entire elephant. And that is a problem with research and how we should be approaching it in a more global sense of understanding. This is another study on a baby burn, and after 5 treatments, the recovery. This is a much newer version of the technology on a burn, a 3rd-degree burn. Another case, that's the day after, and then after 4 treatments. Now, there is a new, the new trend in research that they talk about how inflammation breaks down cellular communication, and they talk about the aging. We're talking about how free radicals lead to aging. Now we're talking about how inflammation leads to aging, and how inflammation will interrupt cellular communications. Inflammation is, of course, is a protagonist in acne, and for young people and old people, mostly young people, obviously. And this is all the aspects you see in neuropeptides. You see them in the regulation, you see changes in lipid biosynthesis, and all of this basically prove how the acne is primarily the main reason that inflammation is what basically underlies acne.
Just to let you know, 2 minutes left.
Yeah. Now we have here the very important aspect, STAT3 and STAT5, of how they can be related in the healing. And this is some clinical studies on acne. STAT3, the signal transducer activator of transcription 3, is required both for the wound healing but also for hair growth. And you can see how here the dependent STAT3 has the greatest hair growth, whereas there is a degeneration of the hair growth when there is an independent STAT3. Very important, regulatory T cells that are generally controlling inflammation are very important. Without them, the stem cells that come into the area to create more hair do not work. So its inflammation is deleterious to hair growth. This is, again, a lot of research, and you can see how different proteins can be negative and other proteins can be positive, and different research shows you basically, I don't know how I got to that. I'm sorry, I don't know how I got to this. I think I went somewhere, sorry. And this is more basically negative effect on our hair growth and how different proteins affect that. Another one. This is some research of before and afters. This is the before, this is the after on hair growth. I'm not sure what's going on here. It keeps going back for some reason. Can you help me? I press it and it goes to the all the way to the beginning or something. I'm sorry about that. Okay, that's another study, hair growth, a third one. And this is basically how it works. How do we start the video here? Okay, so the cellular apoptosis in aging leads to disrupted signaling and basically disintegrated communications. And what signaling technology will do will insert artificial signals at proprietary low energy below thermal noise to basically, there's a mathematical proof that those very, very low energies, which is the exact opposite of lasers, actually will allow the signals to come inside the cells, so to enhance the signals of cells that has deteriorated with age, or basically fill in gaps in signals that have broken due to aging or disease, to kind of enhance communications and enhance the repair and regeneration that would lead to repair of signaling pathways. And by signaling repair and repair of the signal